So I'm very happy this week to introduce Johanna to everybody here at Monash. And there is a lot to say about Johanna. I will try to keep it simple. So after her PhD, she accepted the Carnegie Origin postdoctoral fellowship from 2017 till a few weeks ago, I believe. She held a NASA Hubble Fellowship based at the observatories at Carnegie Institution for Science in Pasadena, in California. And now she is a staff scientist at the Carnegie Earth and Planets Laboratory in Washington, D.C., right? So I think that you, Johanna, have relocated only a few weeks ago, because when I contacted you the first time to invite to this talk, you were still in California, and you were about to relocate to Washington, so you accepted to be here today, even if the larger the time zone is not helping much. So yeah, so that's why we had to anticipate everything. So I usually thank all the speakers, but I'm particularly grateful to you, Johanna, because I think it's 8 p.m. now here in Washington, D.C. So thank you for doing this. So Johanna is doing research on a topic that I consider one of the hottest topics in astronomy during the current decade. In fact, she's interested in studying the physical properties of planet populations and also the chemical environment for planet formation. I think this is really interesting because among all other things, these help us to understand more about the condition of life elsewhere, right? So I think that Johanna will talk about this today as well, and about a survey that she has devised to answer some important questions related to this topic. So before leaving the word to Johanna, I just want to remind how this colloquium works. So Johanna will talk for about 45 minutes, 50 minutes, and then we will have time for questions. So questions are always welcome. And if you want to ask a question, please raise your hand and wait till I don't ask you to speak, so we can keep an order on this. So, okay, thank you, Johanna, and let's begin.
Okay, so I will, let's do share screen here. All right, can you see my first slide?
Yes.
Okay, great. All right, so good morning to you. I'm very happy and grateful today to get to tell you about this new survey, like Lorenzo said, that I'm helping lead, which we're calling the Magellan-TESS Survey, or MTS. And this is a statistical survey of small planets that we're conducting to learn more about what factors impact the planet's formation pathway. Oops. There we go. And oops, no, okay, too fast. We want to understand this formation pathway for these small planets and whether that pathway splits or diverges at any point. I want to acknowledge NASA for financially supporting this work, as well as the rest of the MTS team, especially my amazing co-Is, Sharon Wang and Angie Wolfgang. First in my talk, just to get everyone on the same page, I want to go over how we learn about exoplanet compositions. So I'll be talking a lot about that in this talk. Next, since this is mostly about small planets, those between the size of Earth and Neptune, I want to motivate a little bit why you should care about that kind of planet. Then I'll dive into this main research effort that I'm working on right now, which is this statistical survey of small planets to learn about their compositions and what that implies for their formation. Finally, whenever I go to a movie theater, I always really like seeing the previews for new movies coming. So finally, I'll outline what I think are some interesting upcoming opportunities to understand how unique Earth and the solar system are in the galaxy. Okay, so first, how do we learn about exoplanet composition? To set the stage, here I'm showing plots of orbital period of planets in days versus planet radius in Earth radii, or planet mass or minimum mass in Earth masses. And I'll describe in a minute why sometimes we can only know the minimum mass of a planet. As you can see, we now know of this large and diverse sample of exoplanets around other stars. And those we have found so far are mostly not like the planets in our solar system, which are the red dots on this plot. So knowing that exoplanets span such a wide range of parameter space, how do we start to use observations combined with models to pin down what exactly they're made of? So first I'll start with interior composition. And we learn about this by estimating planets' bulk densities through their masses and radii. So first, planet masses are measured primarily through the radial velocity or Doppler wobble technique, where we observe their very small changes in the star's orbit due to the interaction it has with orbiting planets by observing the small changes in the star's spectral lines as it moves towards us and away from us. Just for reference, hot Jupiters have RV signals in the tens to hundreds of meters per second, whereas Earth induces a signal of 9 centimeters a second on the sun. So big difference. These types of observations are made from the ground, and we're measuring the projected velocity towards us. So there's a dependence on the inclination, and we measure the minimum mass of the planet as m sin I, unless we know the inclination from other information. The main instrument I've been using to make these mass measurements is the Planet Finder spectrograph on the Magellan-TESS telescope at Las Campanas Observatory in Chile. PFS is this great collaboration between these two Carnegie departments with instrument builders, Steve Scheckman, Jeff Crane, and Ian Thompson at observatories, and Paul Butler at EPL. And now we're actually collaborating with, I think, people at almost every Magellan partner institution as well. Here are 2 views of PFS. So hopefully this video works. This side at the bottom left faces the telescope, and that black box is where the light comes into the instrument. You can see Jeff and I flushing out the thermal control system in this video and adding more of that pink liquid coolant. The other side has a panel that we occasionally remove to do work inside the instrument. And here again, you can see Jeff and myself and the wonderful LCO staff installing a circulation tube to help keep the instrument's temperature stable. In the last few years, we've made a few minor and a few major upgrades to the instrument to really help it shine. And I think right now it's really one of the world's prime instruments for measuring exoplanet masses. All right, so that's the mass. Now to get that density and learn about interior composition, we have to get the radius. And this is primarily done through the transit technique, which, as I'm sure many of you are familiar, was used by Kepler to detect thousands of new exoplanets. And here the planet passes between the observer and the host star, periodically blocking out a tiny fraction of stellar light. The measurement here is the ratio of the planet to the star's radius, or RP over R star. And for reference, hot Jupiters typically have transit depths around 1%, whereas Earth around the sun has a transit depth of less than 1/100th of a percent. So for medium and large planets, these types of observations can be made from the ground, but are often made from space with telescopes like Kepler and its successor, the Transiting Exoplanet Survey Satellite, or TESS. So that's interior composition. Next, I just want to briefly go over a few other ways we learn about exoplanet composition. So atmospheres, that information comes mostly from those same transit observations, but instead of just observing at one color, we disperse the light and look for changes with wavelength. So the transmission spectrum here is measured as the planet crosses in front of the star, and it's sensitive to the scale height of the atmosphere, which is a quantity that depends on the equilibrium temperature of the planet, or how hot it gets from the stellar radiation, the planet's surface gravity, which comes from the mass, if we know that, but otherwise we have to assume that, and then the mean molecular weight of the atmosphere, which is what depends on its composition. The emission spectrum of the planet represents the reflected light and thermal emission from the planet when it's directly behind the star, so the planet's day side. And these observations are most sensitive to, as you might expect, temperature, the thermal emission coming from the planet, and also its albedo or reflectivity. All right, taking a step back even further, we think that the composition of stars around which planets form to some extent influence the type and or frequency of planets that form. So typically we learn about host star composition using medium or high resolution optical, sometimes near infrared spectra from ground-based instruments such as these from Keck high res, shown in the different colors for different temperatures. And we measure those absorption lines in the stellar atmospheres and combine those with models and derive relative atomic abundances. So one example of host star studies from my own work builds on one of the most obvious examples of a relationship between stellar composition and the types of planets that form. So in this plot, I have at the bottom the host star metallicity relative to hydrogen. So the iron abundance relative to hydrogen, and the bracket notation is relative to sun on a log scale. So the sun is at 0. And then on the y-axis is the fraction of stars with mostly hot gas giant planets. This paper was from a while ago, before a lot of the smaller planets were even detected. And so we think this relationship comes from the fact that giant close-in planets are influenced, or that the metallicity of the star is indicative of more solids in the protoplanetary disk where the giant planet is forming. And that means the planet can grow bigger and also in enough time to accrete the gas that is still surrounding it in the protoplanetary disk. We also know from studies of transiting exoplanets, which are the blue points in this plot, as well as the solar system planets, they're a little bit harder to see, they're the white squares, that giant planets with more total mass, so total mass in the planet is on the x-axis, these planets also have a higher fraction of heavy element mass, and that's just, not hydrogen or helium. So I was curious, looking at these two relationships, between the fraction of giant planets and the host star metallicity, and then the fraction of heavy elements in a planet based on its mass, do metal-rich stars make more metal-rich planets? The short answer is basically no, at least based on these observations. There was no clear correlation between the stellar metal content, which is here just a compilation of 6 elements heavier than hydrogen and helium, and the planet residual metallicity on the y-axis, which is just the metal content above or below what's expected based on this light blue relationship. So a linear relationship between this host star metallicity and the residual metal in the planet is a prediction of formation models. Formation models think there should be a relationship such that if there's twice as much metal in the feeding zone of a forming giant planet, which you might get by proxy of the host star composition, one might expect that twice as much metal would end up in the planet. So planet formation is very complicated. So perhaps more detailed disk processes, such as the radial drift of grains, might affect this relationship by controlling the solid surface density in the disk, and maybe creating pockets where metals are enhanced and planets are forming there. Really, the cause of the lack of a linearity in this relationship is not known, and should be considered a question in planet formation theory to be further explored. However, this is what was really interesting to me. We did see a correlation between that same residual metal parameter of the planet on the y-axis and the ratio in the star of volatile to refractory elements. Because volatiles are relatively abundant and also can exist in both the gas and solid phases, we had hypothesized at the beginning of this project that volatiles might affect planetary metallicity differently than refractory elements, and maybe we're seeing evidence of this. So following up these cool giant planets to measure their atmospheric metal content would be interesting to test if the atmospheres also show trends with host star composition. And so that may or may not be a JWST proposal that we're trying to put forward. All right, now that you know how we characterize exoplanets, let me briefly motivate a little bit why you should care about this specific population. Coming back to this diagram, I've shown here a few rough categories of planets detected so far, mostly based on period and radius, since this is the population that we have the most number of planets for. We know of more planets that have radius measurements than just mass measurements alone. And the small planets I'm referring to kind of fit into this pocket in this diagram, super Earths and mini or sub-Neptunes. So why are those particularly interesting? Well, as I just said, they fit into this space between rocky and ice giant worlds, unlike anything detected in our solar system. This histogram is from Kepler observations of FGK dwarf stars at host planets. And it shows that the occurrence rate of these small planets is actually the highest. So they're the most common, but naturally fit into these two subgroups as defined by their radii and the apparent gap or dip in occurrence rate between the two sizes. So I feel like we should try to understand the physics behind this most common outcome of planet formation, and also understanding why most stars do and the sun does not have this type of planet is, I think, important for placing our solar system in the broader context of exoplanet systems. All right, so second, while we only have a relatively small number of small planets with both masses and radii measured, and thus bulk composition constraints, even this limited sample shows a wide range in potential bulk composition. So the symbols of the dots in this plot don't matter so much. They're different properties of the planets. But what matters here is if you look at these different colored curves, they represent different bulk compositions of the planets. So something like 100% iron, who knows if that's actually feasible? I'll talk about that a little bit later, all the way up to more and more volatile contents of planets. So I think this dashed blue line is 100% water, approximately. And you can see that at any given radius or at any given mass, there's a spread in this diagram. So how did this variation come to be? Could these planets have formed in different ways to come out with these different compositions? Third, unfortunately, it's still very challenging to even detect planets with masses, or radii, or temperatures that are very similar to the Earth. You saw in those radius orbital period and mass orbital period diagrams that the Earth space was not very populated. And that's just due to the small signals that they induce on their host stars. But there are now many nearby 1 to 3 Earth radii planets that we can study in detail and still use to learn whether conditions a little bit different than the Earth might still produce habitable environments. So I agree that now is kind of the golden age of studying super Earth and sub-Neptune planets to address questions like, what are the rock to water to ice ratios in these small exoplanets? Did they form with those ratios, or were the ratios altered over time? And what can composition tell us about the possible formation and evolution mechanisms of these small planets? All right, so as astronomers, we have limited information. And so we would like to use mass and radius observations of these planets to start to tease out answers to some of those questions that I just mentioned. So here I'm showing just a few examples of ways that people have tried to do this. So on the left, we have a mass radius diagram. The black dash line is originally from Weiss and Marcy et al., 2014, using the Kepler sample. And fitted with just a power law via least squares regression. This entire plot is from Angie Wolfgang's 2016 paper, where I believe she was the first one to fit a probabilistic mass-radius relationship evaluated within a Bayesian framework. And so those are the colored lines here. Also with, I think, a little bit updated data. And more recently, last year, Neil and Rogers actually incorporated period. So this is a 2D plot, but they also used the planet's orbital period in a hierarchical Bayesian model with different subpopulations of planets. And so here you can see they think the data suggests actually 3 populations of planets, one that has a gaseous or volatile envelope, and so the radii are larger. But then at these small radii, they find evidence for 2 populations, one of evaporated cores of planets. They used to be in the blue population, but they lost their atmospheres. But also a population of intrinsically rocky planets that didn't form with that envelope. So point being, mass-radius relations such as these have started to help us separate out different populations and just practically could potentially allow us to make just one of the measurements of just mass or just radius and then still be able to estimate planet compositions, which would be kind of cool. However, studies of small planet masses and radii up to this point have still been limited by a few factors. They haven't taken into account the effect of selecting different or potentially biased in some way samples of planets. So for a super simple, not exactly reality example, but I think it gets the point across. If in this plot of planet period versus radius, here the points are colored by the host star brightness. If I only selected the planets from this diagram with bright host stars, which is a common selection for making mass measurements, you can get a higher signal-to-noise observation more quickly, then I would miss some of the structure in that radius period parameter space. So here you can see there's kind of like a backward C or a J shape, and I get some of that with the bright host stars, but maybe not all of it. So this is a limitation that remains in existing mass radius analyses. Additionally, how the exoplanet mass measurements are actually taken can bias the masses we derive. So as scientists, we like high confidence results. We want to be as sure as possible. And it's a common practice to observe planet RV signals until the signal is found to be non-zero at some significance, like 5 or 6 sigma. And then stop observing. You know, you have your answer, check. But if you think about it, it's easier to get a higher sigma result if the value of my result is also higher. So 4 plus or minus 1 meter per second is a higher sigma result than 1 plus or minus 1 meter per second. So even if I know the orbital period of the planet, like in this cartoony example, if I don't know the mass and I'm looking for a high confidence result, especially with as few observations as possible, right? We're trying to be efficient. I'm more likely to find the larger semi-amplitude to be significant sooner and then settle on that as my answer, even if the true semi-amplitude is lower. The basic idea here is that I'm more likely to overestimate the answer instead of underestimate it. And this systematic bias could shift exoplanet masses towards higher values, making us think that they're more dense than they actually are, which is obviously not good for making accurate studies of these planets. So my very cartoony example is just summarizing this nice paper by Ben Monte, in which he simulated RV observations of stars at random phase and with measurement uncertainty equal to the planetary signal size, so 1 meter per second. And he showed that if RV observations are stopped, so this left plot, once this 6 sigma stopping criteria is reached, this biases the inferred masses towards larger values. So this is the semi-amplitude. He's inputting 1 meter per second signals, and you can see this is not, it's biased towards larger values. And the bias becomes even more extreme when the stopping criteria must be achieved within some number here, 60 observations, right? It's very skewed. But he found that this bias can be ameliorated if, instead of observing until a certain fractional mass precision is achieved, stars are observed until a particular absolute mass precision is achieved. And so doing that, if the criteria to end to observations doesn't actually depend on the inferred mass that you're getting from the observations, that results in a much more, much closer to the expected distribution. So, okay, so now you know why super Earths and sub-Neptunes are interesting, some of the questions that are around them, but also some pitfalls to studying them. So how am I trying to address some of those questions in a robust way? Here comes the Magellan-TESS Survey, or MTS, and our goal is to measure the masses of 30 1 to 3 Earth radii transiting planets detected by TESS. And so TESS is this exoplanet survey satellite that's scanning the entire sky, which is great for us because Kepler, while lovely, was pointed in the north and the telescope I use is in the south. And this survey is designed to investigate whether super Earths and sub-Neptunes formed along the same or different pathways by helping constrain the small planet mass-radius relation and adding 3 additional dimensions that we think could be influencing the planets differently. So the first of these is probably no surprise. It's insolation flux. There's evidence that that gap in the radius distribution that I showed you, that histogram, and you have the 2 populations and there's a dip in the middle. There's evidence that that gap drifts towards lower radii at lower incident fluxes for the planets. And this observation fits models of photoevaporation as the cause of that radius gap. But mass measurements provide a more complete picture because photoevaporation actually depends on planet surface gravity, which depends on a planet's mass. And so we think obtaining masses for planets around this gap at a range of insolation levels will really be necessary to test if some planets formed gas poor, like that intrinsically rocky population in the Neal and Rogers mass radius diagram, or where those evaporated cores suffered atmospheric loss to reach their current sizes. And so in the Neal and Rogers work, which is somewhat similar to what we're thinking of doing with our survey, they do suggest that there's a population of planets that actually formed intrinsically rocky and weren't just subject to photoevaporation. All right, so insolation flux. Second, how do planetary bulk densities depend on host star composition? So you must have known this was coming. I talked about host stars before. While most of the spread in that mass radius relation of small planets, remember I showed the colored curves and there was the planets spanned the colored curves. That could be explained by just variation in their volatile envelopes, but it might also indicate diversity in their interior compositions by major twiddle proxy, host star composition. So by comparing the densities of a larger sample of these small planets to their detailed host star abundances, not just metallicity, but things like carbon and oxygen and silicon and magnesium, we can start to get at the role of the birth composition in distinguishing super Earths and sub-Neptunes. So for example, work on the Kepler sample. So this is just based on planet radii. This showed that super Earths, the green lines here, and sub-Neptunes have different trends in these host star metallicity occurrence rate spaces. So in this first column, the short period planets, you can see that the occurrence rate of both super Earths and sub-Neptunes increases with host star metallicity. But at longer periods, while the sub-Neptunes still seem to increase, although it's less steep, the super-Earths either flatten out in this relationship or even decrease, so that at longer periods, if you have a higher metallicity star, maybe you're even less likely to find a super-Earth. So this is just an example. And again, this is using host star metallicity and planet radii, but we'd like to add in both planet masses as well as other host star abundances to these types of studies. All right, and finally, how do planetary bulk densities depend on system architecture? So characterizing the differences or similarities in these planets and their system architectures might help us compare their birth environments and dynamic histories by trying to look for differences, for example, in eccentricities. Also, I think this is really interesting. There are now multiple papers using the Kepler dataset to some extent, suggesting that some small close-in planets have a longer period Jupiter analog, but not always. Interestingly, these studies also imply that if there is a giant planet, it's very likely that there's an inner super-Earth planet. So how might system architecture influence the types of planets that form? Are the super-Earths that have a giant planet different than the ones that don't? There's actually a fairly recent paper that uses planet formation and evolution simulations to suggest that, yes, actually they predicted a difference, that super-Earths that have outer giant planet companions would be higher density than those that didn't. So in our survey, not only are we trying to measure the masses of the super-Earths and sub-Neptunes at fairly short orbital period, we're continuing to monitor these systems with RVs, radial velocities, at lower cadence to constrain these longer period non-transiting planets. So our Magellan-TESS survey, in this, we're trying to account for some of those analysis limitations I mentioned before. This metric shows how we're selecting our targets in this quantitative way. And so it incorporates a range of insolation flux to address that first question about planet densities and insolation flux. The second term is an estimate of the exposure time based on a predicted semi-amplitude of the planet and what we know about PFS precision. We're only considering sub-Neptune and smaller planets. This term actually has us focusing on that fuzzy area between the super-Earths and sub-Neptunes, where we're really not sure what's going on. And we're also just looking at fairly slowly rotating stars, so we can measure a precise mass of the planet. If the star is too quickly rotating, the lines are spread out, and that makes it harder to do the RV measurements. So here I'm showing just what our target selection produces. In this space, I have planet period versus radius. The color of the point is the insolation flux of the planet. And so all these light background points are all the TESS objects of interest, TOIs, in this parameter space. All the circles bigger circles are potential targets for our survey. The lighter ones still need some more vetting to make sure that they're real planets before we start spending precious Magellan time on them. But then all the X's, all those circles, we have mass constraints for all those planets already. And we're working on our kind of, I guess now it's year 1.5, year 1+2 paper to publish all these masses. After selecting our targets, we have to decide how we're going to observe them in a given observing run. PFS is classically scheduled, but we operate in a queue across the entire semester. In creating this observing plan, we consider how targets rank from our metric, the planet parameters, and the observing run length. I have it on a backup slide because it's sort of complicated, but we use a quantitative decision tree to make sure we get high cadence coverage of the planet across multiple periods, and then ramp down to a trailing cadence, which was once per run, to keep searching for those longer period companions. As part of this decision tree, we switch to trailing cadence when an absolute semi-amplitude precision is achieved, not that fractional precision like 6 sigma to avoid the mass measurement bias I mentioned earlier. And to the best of my knowledge, I think we're the first exoplanet survey to incorporate these bias mitigation approaches in our survey design. Oh yeah, I forgot to hide it. So this is our decision tree, but the details don't matter. It's kind of scary looking, but it's quantitative. That's the important part. All right, so while the goal of our survey is a population level study, each planet is really its own beautiful butterfly that is interesting for individual study. And so the colored names of these TESS objects of interest on this plot indicate cases where we have led or contributed data to individual system publications. So the one that I recently led was TOI 652. And this is a 4-day sub-Neptune planet that's located right above the radius gap, so right on the higher end of it. And it has a bulk density that's low enough to suggest that the planet has at least a small volatile envelope. So this system could be interesting, and actually was in a recent HST proposal for atmospheric studies, because it could have a water-rich atmosphere and its high equilibrium temperature, so it's on the hot end, indicates that most condensates or hazes in the atmosphere wouldn't be present. So we'd be less worried about having those hazes or condensates mute out or flatten out spectral features. This is also a really interesting system because it's one of those super Earths or sub-Neptunes that has a Jupiter analog planet companion that was detected before TESS detected this planet. So did that outer planet affect the formation or composition of this inner planet? Ground-based observations have been proposed to measure the spin-orbit angle of the planet. So if the orbital plane of the planet is misaligned with the spin angle of the host star, that might be indicative of scattering processes in the planet's formation versus a smooth disk migration. I also just wanted to, I thought this was kind of cool. In this community organized HST proposal that TOI 652 is part of, it also includes 4 other planets that PFS was also helped contribute data to measuring masses of. So it just shows that PFS is really a prime instrument for these small planet observations. All right, so the next slide is a little busy, but it's really just like a show and tell. So brace yourself. The numbers and yeah, all the data on this, the individual values don't matter so much. I just wanted to show off our beautiful PFS radial velocities. So you can see on the y-axis, the type of semi-amplitudes that we're measuring. In these plots, a white noise stellar jitter error term has been added to the points, but in many cases, our PFS data have internal errors significantly less than 1 meter per second. So I couldn't even fit all of them on the slide. We have mass constraints on 18 planets out of our hopefully 30 for the full survey, which is well matched to having used about 60% of the time we estimated for a 3-year survey, which now it can't be 3 calendar years, but that's okay. It'll just have to go a little bit longer in calendar terms. All right, so that's how we get the targets and what our data looks like. What about the types of inferences we can make? When we compare the Wolfgang et al. Relation, shown here with the observed data at the time, we already see that our less biased and uniformly derived measurements confirm that there is intrinsic scatter, astrophysical scatter in these planets in the mass radius space. Here, the shaded region shows what is predicted from the Wolfgang 2016 mass radius relation. And these are our preliminary mass measurements. We're definitely still tweaking them. And I'm happy to talk more about that. That's been an adventure. Here I'm showing the same data, except with ellipses indicating the 1 sigma confidence intervals for the masses and radii. In this plot, the radii are just the TESS project radii. So one of our to-dos is to fit the TESS light curves uniformly. But overplotted again in blue is the Wolfgang mass-radius relationship. In red is another common mass-radius relationship, Chen and Kipping, 2017. But here I've added in black the mass-radius relation that we derive from our data using the same prescription as Wolfgang et al. 2016, but just with our data, which, as I've described, we think is at least, we're trying to account for potential biases that might have existed in previous data sets. So you can see that this mass-radius relation in black mostly overlaps, especially at the lower end, but is somewhat narrower. So the dotted lines are 1 sigma errors, and also not quite as steep. So anyway, this is preliminary. It doesn't include, as I said, uniformly derived radii, which we're in the process of constructing from the test-like curves to try to account for factors like correlated noise and crowding around the star in a uniform way across all the light curves. And for this first year, 1.5 paper, we're also going to incorporate an insolation flux dependence on our modeling, similar to the Neal and Rogers approach. And finally, something that I think will really set our work apart is accounting for how our targets were selected from the parent population via that metric equation that I mentioned before. All right. I wanted to end with a preview of what I think are some exciting prospects for moving further along the path to characterizing potentially more Earth-like planets. So here's roughly where we are now. I spoke in great detail about this robust study of planet densities, but the interior composition is just part of the story. I'm also interested in how small planet atmospheres might also hold clues to their formation scenarios. Right now, we just don't have many small planet observations, and so it really, of their atmospheres, and so it really remains an open question whether there's a transition between planets with and without atmospheres. How sharp this transition is, or even the dominant mechanism controlling the transition. So I talked about photoevaporation affecting small planet atmospheres, but another theory that's been proposed is core-powered mass loss. And furthermore, it remains unknown to what extent the planets on the small end of this distribution have secondary atmospheres, such as from outgassing. So luckily, as I've just described, we've built the perfect sample with MTS that will provide both the base target list and the planet masses that we need to interpret atmospheric spectra. And so we're hoping to propose for J2ST observations to quantify this fundamental but actually not very simple question, which is there a clear boundary between observable atmospheres and not observable atmospheres, by which we just mean below some noise floor that J2ST can reach? And what atmospheric factors contribute to that boundary, like clouds or haze or the atmosphere metallicity? For example, I would have naively thought that in this planet radius versus atmosphere amplitude space, that the smaller planets would have had smaller features and the larger planets would have larger amplitude features, the opposite of the trend shown here. However, if metallicity is a factor in controlling the variation in small planet atmospheres, maybe we would see a trade-off between planet radii and metallicity, with some larger planets having higher atmospheric metallicities that then reduce their scale height and thus the amplitude of their atmospheric features. This is just a complete toy example. We really don't know what we'll find because, like I said, small atmospheres are still fairly uncharted territory. But it would be great if we could make this a multi-cycle J2ST program, so we can also start to test how this transition from no atmosphere to having an observable atmosphere depends on the planet's insolation flux, its current insolation flux, as well as the stellar effective temperature, which we think could be a proxy for the level of high energy radiation the planet experienced early in its life. So that might have contributed to the atmospheric loss. Ground-based optical observations of planet atmospheres might also be important for helping answer these questions, especially if there are clouds or hazes, because the optical observations could help constrain the scattering regime for the planet atmosphere. And luckily, again, sort of built in, many of our MTS targets are bright enough and have large enough transit depths that optical observations of their atmospheres might be possible from the ground. So we could get complementary data. So overall, clearly don't have the time yet, but if we had a Magellan-TESS JDOS-T survey, I really think it could be groundbreaking in the population level approach to studying small planets and the robustness of the conclusions that would be possible from this data set. And I also think it, by answering sort of this fundamental question about does it have an atmosphere, does it not, and what does that depend on, that could help inform how future observations of small planets are conducted to help us make the best use of expensive telescope resources. So that's like my exciting plan for myself for the next few years. We'll see. All right, so I've been talking all about astronomical observations, but really they're quite limited. In reality, we have mass and radius and maybe host star composition. So how do we know that we're interpreting these correctly? One of the things I'm really looking forward to at Carnegie is collaborating with my geophysics and geochemistry colleagues to estimate more accurate interior compositions by conducting experiments to see how different materials behave at the temperatures and pressures of these super Earth and sub-Neptune planets. So most of the data that these types of composition curves are based off of is very Earth-centric. It's much harder to get to these extreme conditions. And so, for example, in this study, using NIF Lawrence Livermore data, the authors showed how they're measured in blue down here, iron equation of state compared to different extrapolations. And you can see there's a spread. Okay, it's not that big. We're kind of zoomed in here. But as astronomical data grows in number and in precision, it'll be increasingly important to really ground our astronomical observations in this type of experimental work to know how to interpret them. All right, I also think it'll be important to dig deeper into the role of other planets in shaping small planet systems. So I think you could probably tell I was excited about this before when I was talking about it. On the one hand, like I said, it appears that about 1/3 of small planets have a Jupiter analog companion, and that these systems are more frequent around higher metallicity stars, right? Giant planet, they like high metallicity stars. Perhaps giant planets in these systems played a similar role as Jupiter in our solar system, influencing the architecture and composition of the inner small planets. On the other hand, from different studies, it appears that at longer periods, so slightly longer periods, but still small planets, which should be immune to the high energy stellar radiation that could be blowing off their atmospheres, these are more frequently found around lower metallicity stars, where, as we know, giant planets are rarer. At these longer orbital periods, the planets in this study were still large enough, and we assume massive enough, to have accreted a gas envelope if the gas were there. So the fact that they didn't indicates they probably formed after the disk dispersed. So they were really this boron rocky sample. Perhaps in a late stage of accretion, a late stage of formation similar to the giant impact phase of Earth and Venus. So really, is Earth-like planet formation more common when in the high metallicity case, where you have an outer giant planet, or in a low metallicity case. I'm just really interested in exploring the role of system architecture further with a survey specifically designed to address this question. For example, trying to control for metallicity. I'm also really excited about the increase in exoplanet atmosphere characterization, ramping up from the ground. And so one example of that, hopefully in the not too distant future coming to Magellan, is actually an instrument that's being built for GMT NIRS, but it's supposed to first come to Magellan and be called MAGNIFIES. And this is a high resolution, wide wavelength coverage infrared spectrograph. And it would be perfect for measuring detailed compositions of exoplanet atmospheres from the ground, maybe like those cool giant planets that appeared to have higher metal contents when their stars had a higher volatile to refractory ratio. Be my backup plan if JDOS-T proposal doesn't get accepted. Something like MAGNIFIES also covers this metastable helium-1 line, which has recently been shown, here's an example of observations, to be a powerful diagnostic of hydrodynamically escaping planet atmospheres, which, given the short orbital periods of many planets, is probably a common process, but we need more observational constraints to really understand it better. These are very, most of these papers have only come out in the last 2 years. I also recently joined the science team for this MIR-MOS instrument, so Magellan Infrared Multi-Object Spectrograph. And one of the things that excites me about this potential instrument is that it would kind of take a leap in technological capabilities for measuring exoplanet atmospheres. So you may have heard of these studies using this beam diffuser in photometric instruments. So the left image is defocused, as is common for spreading out the light over more pixels on the detector to increase sensitivity, but there's lots of correlated noise. You can not defocus the image, but then you might get saturated and it's still not a very stable image. But this shows, the right image shows, instead the use of this new beam shaping diffuser, and that both spreads out and stabilizes the stellar light. So the proposal for MIR-MOS is that we would use this beam shaping diffuser in a spectrograph, which I think hasn't been done before. That would increase MIR-MOS's capacity to measure atmospheres of more precisely of planets and perhaps smaller planets. So here's an example of a comparison between MIR-MOS and something like JDOS-T or HST. So anyway, that's something cool maybe coming in the future. Moving into the era of 30-meter class telescopes, it'll be important to develop a coordinated approach for using things like Magellan and GMT. Ground-based RV programs like PFS are already helping to detect small habitable zone planets around low-mass stellar neighbors. And so we can use GMT to measure reflected light spectra of these types of planets and deduce potentially biosignature abundances like O2 and water and methane. I'm almost finished. Finally, looking even farther into the future, all these insights gained from this prior work on what Earth-like systems look like can be applied to new detections of true Earth analog planets, temperate terrestrial planets around sun-like stars. And so this is going to require something like LUVOIR or HabEx. But to enable these space-based telescopes to make the largest number and highest signal-to-noise observations, we really want to find the planets that they would observe ahead of time. And this is what the NASA NSF Extreme Precision Radio Velocity Working Group was trying to figure out how to do. And so I encourage you to read that report. We had lots of recommendations for instruments and technology development. Personally, I'm kind of interested, there's this instrument GCLEF that's supposed to go to the GMT, Extreme Precision RV instrument, but similar to MAGNIFIES, there's talks of just bringing GCLEF to Magellan first. Most of the stars that something like LUVOIR is going to survey for Earth-like planets, those stars are really nearby. So they're really bright. And so you don't necessarily need the aperture of GMT to start doing this precursor survey. And just besides finding the Earth twins, these types of instruments can also provide the mass measurements needed to interpret the space-based observations, and also provide very precise planet densities that could serve as benchmarks for the geophysical models. All right, finishing up. So ultimately, take-home message is I'm interested in following this path, which I think is beginning now with the statistical Magellan-TESS survey to explore whether these super Earths and sub-Neptunes have differences in their formation based on these different parameters. And I think this is leading to an advance in our understanding of how these small planets formed and how similar or different they are from the Earth. So please look out for our MTS years 1 and 2 paper out, hopefully later this year. And hopefully many more interesting offshoots of this project on small planets to follow. So with that, I will stop and take any questions.
Thank you, Johanna. It's really interesting. So I think since we started 5 minutes later, we have still time for a few questions.
Okay.
So if someone has a question, please raise your hand. Yes, so Andy, please.
Hi, Johanna, that was great. It's really interesting to investigate the radius gap, but from what you were showing with what Ben Monte showed, is that so for example, if there were other features in that diagram you want to explore, then a case could be made for trying to get the most accurate absolute masses for all systems rather than just in this particular feature that you're interested in. Mm-hmm. Are there other possible features in that space that might be expected from theory where you could make a case for actually just trying to get more absolute accurate masses for everything rather than just investigating this particular feature? Say if you had, many stars.
Yeah, nothing is coming to mind exactly. I mean, what's gained a lot of traction is this 3D space of mass-radius-insolation flux. And Ryan Cloutier who's at the CFA, has some interesting work showing, I'm not gonna remember the details, but basically for M dwarfs in particular, there are different predictions of the formation of those planets and how photoevaporation versus something like, I think, core-powered mass loss, how that might change the slope of that radius gap with insolation flux. And so in particular, his work shows that M dwarf planets might actually be the fastest route to better understanding the processes or the dominant process between the radius gap. And so that's one example of, I mean, he's still studying a population of just M dwarf planets, but yeah, it's not just within a specific radius range. I don't know if that answers your question.
Yes, it does. Thank you.
Okay.
Great talk.
Rosemary?
Oh. Hi, Johanna. I could stay here all day asking questions. I won't annoy people with that. I'll just make a comment following up from Andy's thing, and then I'll ask my question.
Okay.
This gap, well, it's been known in the mass distribution from Mordicini et al., people doing planet formation studies. That's been known for a long time, and so they understand why it's there from a theoretical point of view. And I don't think, insolation surely affects systems very close in, but I think that gap's there anyway, whether you're close to the star or not. Anyway, my question was, and I'll mention Kepler 36, about Kepler. I won't talk about Kepler 36 too, but anyway, lots of information in there. My question was going to be about your planet finder spectrograph.
Oh yeah.
Looks like it's not in vacuum, is that right? Right, so how does it compare to the ESO, the European instruments, HARPS, and even more spectacularly, the espresso spectrograph on the VLT?
Yeah. Yeah, so I failed to mention, I apologize, PFS is an iodine cell radio velocity spectrograph, so that's what we're using for calibration, not the absolute type of calibration that HARPS and espresso are using. Yeah, no comparison. I mean, yeah, espresso is blowing everything out of the water, so certainly espresso is doing better than PFS, but PFS is pretty comparable to HARPS at this point, and occasionally, I mean, depending on the system, doing better and how we take the observations. We actually recently, within the last few years, upgraded our detector and started using a narrower slit. So now we're operating at a default resolving power of around 130,000, which is, I think, a little bit higher than HARPS. And we started a strategy which I think Xavier de Musc originally advocated for, which was taking at least 10-minute observations of stars to average over the P mode oscillations, and then, you know, splitting those up so you take 2 observations or 3 observations per night. So we've seen improvement in precision adopting some of those strategies.
Yeah, good. Well, so many beautiful things to do.
Yes.
A feast.
Any other question?
Actually, I have one question. First, thanks for this very nice and interesting talk, Johanna.
Yeah.
So I have a relatively basic question. You mentioned measuring metallicity of planets or residual metallicity of planets.
Yeah.
How accurate, or better said, how model independent are these metallicities? If I understand correctly, so far they've only been inferred from the mean density, right, for the measured mass and radius of the planet. So I guess you cannot really disentangle between a small dense core and a large atmosphere versus a large, less dense core and a smaller atmosphere.
Yeah, so there, yeah, you're right that for the super Earths and sub-Neptune regime, it is sometimes degenerate in terms of like what you just said about trying to distinguish different parts of the model. But for the study that I was talking about, we were looking at giant planets. And so that modeling is based on the mass and radius and to some extent the age of the planet, but it's not as degenerate as the smaller planet interior modeling, and compares fairly well with what we know about the solar system giant planets. So that work is all done by Daniel Thorngren, if you want to look up his work. And so, but you're absolutely right that there's uncertainty in the kind of heavy element mass of the planet. But a lot of that uncertainty is actually driven by the uncertainties in the measured masses and radii of the planet. So at this point, it's still data limited by the precision of the data.
Okay, thanks.
Thank you, Johanna. It's very interesting, everything that you have shown today. I think we should let you go because it's after 9 p.m.
It's okay, I'm having fun.
So no, I just want to thank you again and let you know that really enjoyed to see this science. And yeah, thank you very much for everything.
Yeah, thank you guys. And if anyone has any other questions, please feel free to email me or get in contact.
It's great you could come all the way to Australia to give us a talk today.
Yeah. Oh, I wish I could have. I've never been. So.
Oh, well. And thank you for standing upside down while you gave the talk. That was amazing too, so we could see the right way.
I practiced.
Thank you, Johanna. It was good to see you.
Good to see you too. All right. Thanks, everyone.
Thank you. Thank you to